Welcome back to the workshop. Today I've put together a collection of short clips from around the shop that you might find useful or interesting. I hope you enjoy them. And as always, feel free to leave a comment if you have any questions. Have you ever wondered why tool makers grind a relieved area into the top of their vices? That shaded section sits about 0.2 millimeters below the main ground surface. Instead of having to select a parallel to raise a part above the vise for grinding the top face, you can simply flip the vise over and set the edge you want to grind flush with the top. The relieved area then provides clearance for the wheel to traverse along and across the part without touching the vise. If the part stays clamped, the vise can even be rotated onto its edge for grinding the ends square. I often use this method for small sawn stock parts. It's a simple alternative to milling. Quite often, you'll need to check if your parallel is high enough in the vise to allow machining the part to the required height. This small quick check gauge is ideal for that. It gives a more precise reading than a simple rule, and can also confirm that a part is sitting high enough above the jaws when profiling, for example. Dressing smooth, accurate angles on a grinding wheel can be tricky when using a typical close-fitting slide. This setup solves that problem with 2 rows of enclosed, precision-hardened steel balls. They run in 4 V-grooves that are precision ground to give about 0.01 millimeters of interference. That fit removes play in the slide while still allowing a smooth, easy motion. All the working parts are hardened and ground, and remarkably, it's still performing perfectly. almost 40 years since I made it. This dedicated setting block is ground to give exactly 45 degrees on 70mm sine rollers. It looks like I may need to invest in a new wheel soon. Finding the theoretical intersection of two edges is fairly straightforward when they're square, but when you're working with included angles other than 90 degrees, it can get a bit more complicated without specialist gauges. Here's a simple technique I like to use. First, the part is set so the two sides are at equal angles from the datum. Then an end plate is fitted to the sine bar, and round magnets are placed in the V. This setup allows the sine bar to locate accurately on a range of angles, not just 90 degrees. In this example, I use an edge finder to locate the quadrant of the sine bar roller. The DRO is then zeroed. The same operation is repeated on the opposite side, and the DRO reading is noted. Moving the bed to exactly half of that reading puts the tool directly above the center of the angle. Of course, when the edges are square, which is much more common, the process is simpler. In this example, a V ground centrally into a 16mm hardened rod works perfectly. The nice thing about this gauge is that the tilt angle doesn't need to be known. I use a sine square to tilt the part. I prefer it over a sine bar because it has a tall locating edge for long parts and a short, stable base. Once the gauge is located on the corner, the center is guaranteed to be directly above the intersection of the edges. Again, I'm using an edge finder here. Knowing both the radius of the edge finder and the radius of the gauge, it's easy to calculate the exact bed movement to reach the theoretical intersection. In this example, the edge finder radius is 5 millimeters and the gauge radius is 8 millimeters, giving a total movement of 13 millimeters. If we're fortunate, the situation is even simpler and standard workshop tools can be used. In this case, the part again has a square edge. This method works directly when the part is set at 45 degrees, although with a bit of trigonometry, other angles can be worked out too. The nice thing about V-blocks is that their opposing V's are exactly central, which we can use to our advantage. By using a dowel and a DTI, the center of the dowel can be found, which is also directly above the intersection of the edges. Apologies for my hand getting in the way during that part of the clip. Another way to do this is by using the known width of the V-block. In this case, 36 millimeters. This is useful if the block only has one V. In this example, I'm using an edge finder again. Simply find the edge of the V-block and move over by half its width, plus the edge finder radius. So 18 plus 5 equals 23 millimeters. When tapping larger threads in the mill, a sturdier tap follower is much better than a delicate one held in a chuck. For maximum rigidity and minimal height, the mechanism is built into an R8 blank arbor. Using a blank arbor allows for a larger diameter pointer with a longer travel, both of which make the setup more reliable and easier to use. My squareness comparator used to have a round rod, which made it difficult to keep the indicator positioned exactly where I wanted it. By adding a precision linear slide and ball guide, the indicator now stays perfectly centered in the block, and the radius reference curve remains consistent every time.